Hello, welcome back everyone. Today we're going into chapter 5 where we are going to start on antiderivatives and indefinite integrals. So to kind of set the stage for what we'll be looking at in this section, I'm going to list out a few functions, and I want you just to sort of think about which ones have x to the fourth as their derivative. So we'll start with cap f of x is equal to 1/5 of x to the fifth. Cap g of x, 1/5 of x to the fifth plus 19. Cap h of x is 1/5 of x to the fifth plus, that'll do 5,280, number of feet in a mile. So looking through those, you should notice that all three of those have a derivative of just a plain x to the fourth. The 5 and the 1/5 each time cancel, drop the exponent by 1, and on 2 and 3, derivative of the constants are always 0. So all of these have the same x to the fourth derivative. What we're going to be doing in chapter 5 is basically hitting the reverse gear and saying, okay, what are the functions that have this x to the fourth as their derivative? We use this integral symbol to tell the reader that. Basically, this is saying do the antiderivative of whatever I show you. So for this, antiderivative of x to the fourth, and we multiply by dx, indicating that, okay, x is our independent variable. Well, notice all of these had a 1/5 x to the fifth involved. Some of them had a plus 0, some of them had a plus 19, some of them had a plus 5,280, some of them could have had minus 23 trillion, but they would have had some constant attached, so we attach the plus c. If you have trouble remembering the plus c, write it in red or highlight it. Do something to help get that good habit formed, since this is not one solution but an entire family of solutions that all have this basic format and then some constant attached. Now, there's nothing super special about the x to the fourth. This does happen in general with x to a power. Antiderivative of x to some number with respect to the variable x. We're doing the power rule only backwards now, since we're doing an antiderivative. So instead of dropping the exponent by 1, we're going to add 1 to the exponent. And just like before, we do want to sort of cancel that. So n plus 1 times the reciprocal of n plus 1, those will cancel each other out, become a 1. We have the implied 1 here that typically is not written. And again, plus some constant, since there's an infinite number of functions that have this as their derivative. Similarly, a couple other familiar ones, antiderivative of e to the x with respect to the variable x. Well, remember, the derivative of e to the x was e to the x, so this is still e to the x, only now we have our friend the plus c. Similarly, if you recall, the derivative of the natural log of x was 1 over x, therefore the integral of 1 over x dx is natural log absolute value of x, again, plus c. Absolute value just because we want to avoid domain problems. Remember, we can't do a natural log of a negative number. And constants and adding and subtracting work the same way they did back in our derivative days. So if they ask for the antiderivative of, let's say, pi dx, remember pi is just a number. What type of function had just a number as its derivative? Linears did. So this would be pi times x plus c. They could give us integral of 16 e to the u times du. So remember, the variable isn't always necessarily x. Well, just like in our differentiating days, the 16 is just sort of along for the ride, and we follow our now antiderivative rules the same way we would follow derivative rules. So e to the u is its own derivative and its own antiderivative, and then we attach our plus c. So if I have the integral of, let's say, 9x to the 5th times dx, again, just like with the 16, I'll hold on to the 9 and then follow that same pattern doing the antiderivative of the power rule. So instead of subtracting 1 from the 5, I'll add 1 to the 5, which means I'll need a 1/6 here, a plus c, and then we just have a little cleanup there. So 3/2 x to the 6 plus c is our family of antiderivatives. And let's see, then we have, flip the page from the room here. We can have multiple terms happening as well. So if I want the antiderivative of 23 over x plus 7e to the x plus x to the 4th, all of that times dx, I can just take those one at a time. So I'll hang on to that 23. Think of this as 23 times 1 over x, so that is, hopefully you recognize, the natural log. Hang on to the 7. Antiderivative of e to the x is still e to the x. And our third term here, just another power rule. And just remember your plus c. Don't forget your constant. All right. So next up, we'll do a couple that require a little bit of manipulation before we do the antiderivative, but still not too terribly different from what we've just done. So we'll do the integral of 5 over x to the 7th times dx. Before I do the antiderivative, I'd like that as just 5 times x to a power. In this case, I need a negative exponent involved. After that, just the power rules again. So hang on to your 5. X to the negative 7th. Remember, instead of subtracting 1 from the exponent, when we're doing the antiderivative, we add 1 to the exponent. So that brings us up to a negative 6. So I need a negative 1/6 there and a plus c. So this would be negative 5/6 x to the negative 6 plus a constant. Now the nice thing about doing all these antiderivatives, if you want to check your work, just differentiate your answer and see if you come up with what they had. All right, so next one again needs a little manipulation before we do the antiderivative, but nothing we haven't done in our derivative days. So if I want the integral of 18 times the 4th root of x cubed times dx, I need to go to x to a power format. So integral of 18x to the 3/4 power, so exponent is still the exponent. index becomes the denominator of the exponent. Hang on to your dx, we do have to have that. So after that, I'll hang on to the 18, hang on to my x, and again, since we're doing the power rule backwards, instead of subtracting 1, we'll add 1. So adding 1, in this case, is adding 4/4, which would take us to a 7/4 power, which means I need its reciprocal 4/7. And as always, our friend the plus c. So after that, any simplifying that we can do, 18 and 7, let's see, no common factor is there. So then we're looking at 2, 3, 72 sevenths, x to the 7/4 plus c. All right. Let's see, the next one we end up manipulating both pieces, but the ideas are still the same. No brand new ideas in this. Integral of 5 over cube root of u plus u to the 3/5 power times, this time du. This part is going to be quite important later on, so make sure you're bringing that one along as well. So this one, I can't jump in and do the antiderivative yet until I fix that first term. So integral of 5 u to the negative to get it out of the bottom of the fraction, 1/3 to get it out of the cube root. Hang on to your plus u to the 3/5. That one looked fine. Hang on to your du. Again, that guy's going to be important later on. So then we just take it one piece at a time. I'll hold on to the 5. Leave a little room there. U to the negative 1/3. We're doing an antiderivative. So again, instead of subtracting 1, we'll add 1, as in this case 3/3. So negative 1/3 plus 3/3 is positive 2/3. Then we have our 3/2. That way, when we differentiate, the 3/2 times 2/3 is the 1. 1 times 5 gives us the 5 that we had in the previous step. Then on to the next term. Again, the antiderivative has us adding 1, this time in the form of 5/5. So we have u to the 8/5, which means I'll need a 5/8. That way, when I differentiate, 5/8 times 8/5 is 1. We had an implied 1 in front of our u to the 3/5. And then we have our plus c at the end of the line. Okay. So our next one, again, just a little bit of legwork at the beginning of the problem to get us started. The rest of it is pretty much the same as what we've been doing. So this one we're integrating with respect to the variable t. So this one, just a little bit of distributive property would make the problem much easier. So we'll do integral of t to the 7th plus 19t squared minus 2t times dt. My apologies. I'm sure you can hear my 8-month-old. She's with mom and grandma right now. About time for her nap. All right. Antiderivative of t to the 7th. We'll bring that up to t to the 8th, which means I'll need a 1/8. That way we get our 1 coefficient back. Hang on to your 19. T squared is now t cubed. Add 1 to the exponent, which means I'll attach a 1/3 there. Hang on to the minus 2. T to the 1st. So the unwritten exponent of 1 is now t squared, which means we'll attach a 1/2. And since we're doing the antiderivative, plus the constant, and then we're just on cleanup duty from there. So we have an 1/8 of t raised to the 8th power plus 19/3 of t cubed minus t squared plus c. And again, if you're not sure if the derivative is correct, just slap a y equals in front of it and find y prime, and you should get something equivalent to what you started with. All right. So next one is just a quick application, not a very long one. So sometimes they'll give us some information to let us actually find the value of c. We call those initial conditions. So the idea with the initial condition is basically that if we find a family of antiderivatives, and let's say they're just a square function, we could have a plus 2, we could have a plus 1, we could have a plus 0. You need a little bit of imagination. Picture that having the same shape a little bit better than I was able to do. But we're just moving that shape up and down the graph. If they give us some initial point, we can tell which graph to go with. Is it this one? Or if they gave us a point back here, okay, this is the particular antiderivative. So for this one, we're asked to find the equation of the function with the following properties. So dy dx is, what did I pick? Negative 3x. And we know that f of 0 is negative 5. So on this one, they gave us a derivative. They want the original. So in other words, we have to do the antiderivative to get to the original. So antiderivative of negative 3x with respect to the variable x. That will start us off. So the x to the first, again, if they don't write the exponent, we can assume it's a 1, is now an x squared. We have our negative 3 still. Because of the 2 here, we need a 1/2 to cancel it with when we do our derivative. So 2 times a half is 1. 1 times negative 3 is the negative 3 we started with. We have plus c. So for the moment, y is negative 3/2 of x squared plus c. Now we fill in the information they gave us. They told us that f of 0 is 5. So all of our x's are zeros, all of our y's are negative 5s. So negative 5 is negative 3/2 times 0 squared plus c. So negative 5 is equal to 0 plus c. c is negative 5. So the function that has both of these properties, both the derivative of y equal dy dx is negative 3x, and f of 0 is negative 5, would be f of x is negative 3/2 of x squared minus 5. So plus a negative 5, just go ahead and shorten it down to a minus 5. All right. So one more application in the business sector. So this time they're going to start us with a marginal cost. If you recall, marginal cost is a derivative. So our marginal cost is given in this problem as c prime of x is 7/10 of x squared plus 4x plus 1. And they tell us we have a fixed cost of $6,000. That's the ugliest dollar sign I've ever written. Oh, well. So if we want to figure out what the original cost function was, we would simply find the antiderivative. So integral of 7/10 of x squared plus 4x plus 1. All of that is multiple terms, so contains multiple terms, so parentheses and times dx. So I'll hang on to the 7/10 and multiply by 1/3 x cubed. Hang on to the 4, multiply by half x squared. Antiderivative of a constant is a first power, and don't forget our plus c there. So this is our c of x. Unfortunately, kind of in math, sometimes you do see similar looking variables. C of x is the cost function. Just the c by itself is the arbitrary constant. So a little bit of cleanup, and c of x is 7/10 over 3x cubed plus 2x squared plus x plus c. Fixed cost of $6,000. So the idea with a fixed cost is it's something that the business has to pay no matter what. So for example, if you rented out a warehouse to make whatever it is that you're making, whether you made 1,000 units that month or set up an air hockey table and played air hockey that whole month, landlord wants the same amount of money no matter what you did in the space that time. That would be an example of a fixed cost. So for the fixed cost, we're going to say, okay, that happens even if we made 0 items. So in other words, what this is telling us is that c of 0 is equal to 6,000. So 6,000 is equal to 7/10 over 3 of 0 cubed plus 2 by 0 squared plus 0 plus c. So c here is 6,000. So our cost function, c of x, 7/10 over 3 of x cubed plus 2x squared plus x plus c. So that would be our cost function. And then you could use that, of course, to find the cost of any number of items they asked us about. Okay. So that is a good start on our antiderivative. So it's basically hitting the reverse gear on all of our derivative work that we've done. All right, so this came out of section 5.1. The homework would be the same on both the new and old edition. So I would try out 1 to 23, the odds, 43 to 69, every other odd, 81 and 85 also ask interesting questions. Okay, so if you have any questions, please feel free to email me. Otherwise, I will see you next time.